Okay, any guess? Will it increase the variance or it will decrease the variance? Anyone? Yamini, if Yamini is present. Yamini, will it increase the variance or decrease? If you're working on a time series data, this thing you only have to worry about that this direction of these two things, that is your residual are positively correlated or negatively correlated, or this x independent variable is positively correlated or negatively correlated, that you have to first understand to understand the consequence of the autocorrelation problem, and accordingly you have to think about the remedial measures. Okay, Ikra is saying it will decrease the variance. Okay, let's see. If this thing is positive, means you multiply this positive to positive values, this numerator will increase, right? If both are positive. In the denominator, it depends upon these fractions, that how much we have. Like in this case, this particular value is 1 minus 0.35, so that is 0.65. So this denominator is 0.65 and numerator is more than 1. Like here, this is 1.35, right? Divide by 0. Now this division, if this division is in fractions, then it will decrease, right? But if it's more than 1, then it will increase. So this is also depend upon these two values, that how much correlation they have. The more correlations are there, the more the impact of this particular thing, but it may cancel out depend upon these two directions. Yeah, but that also depend upon these two. Like, let's suppose I take another example, 0.9 and 0.9. Now in this case it's by 1.81, and in denominator now it is 0.19. So in this case, definitely value is going to be more than 20. It's more 8 or 9 times, right? So this will increase, multiply by 8 or 9. So that's the thing, that how much these correlations are, these values. If it's less, for example, it's 0.3, 0.3. So in this case, the numerator is 1.09 and division it is 0.91, right? So this value is 0 point something, right? So in that case, it won't increase, it may decrease. So it depends upon these two correlation factor, how much they are correlated, and also on their relations, is it positive or negative? Like if it's negative, like again take example of 0.5 and 0.5. Let's suppose this particular correlation is negative. So now in numerator, we have a 1 minus 0.35, and in denominator we have 1 plus 0.35. So it will definitely decrease the variance. If this relation is opposite, that may decrease the variance. If they are positively or negatively, both are in the same direction, then it depends upon the how strong correlation they have. If it's too high, variance will increase. If their correlation is too low, it's a correlation of x with the lag value and u with the its lagged values. If it's too low, variance might decrease. So these things you have to keep in mind, that how strongly they are correlated with their lagged values, and is that they are in opposite direction although that's a very rare case, they're going to be in the same direction. Reason is that because u hat is y minus the intercept minus the slope coefficient of this x variable. So they're going to be in the same direction. The relation of their lagged values maximum time is going to be in the same direction. So it means that depend upon their correlations. Is it clear? This consequence that how it will affect the variance of our estimate. Anyone any doubt in the consequence? I told you there are 4 or 5 different combinations. These combinations you have to test, and then you get this idea in which situation it's going to increase and which situation it is going to decrease. Means like heteroscedasticity and verticality, there is no single answer for this thing. It totally depends upon these two relations. This x with its lagged value and residual with its lagged value. Okay, so if the consequence is clear, now I'll come to few detection methods today. And other methods we will do in the next class. But before that, I suggest you make a list of all your variables and try to practice these things in the STATA. Because if you are doing with the class, if let's suppose you have any particular difficulty transforming the variables or in any particular command, then I might help you in that case if I know that command. Because many times the softwares have the commands that we don't know and we do it in a manual process that take a much longer time, like this creation of dummy. In this data, with a single command, you create the dummies and that save a time. I had this experience with one of the guy from Central University of Srinagar. Maybe I have discussed this earlier. Actually, what he was doing, he needed a dummy variable from this NSS, so unit level data. And he was creating dummy in a manual process, like giving 1 0 1 0 1 0, and he spent 1 week just to write the dummy variables in a STATA software. And later on, I told him that you only need to write one single command and STATA automatically create the dummy variables. There are so many incidences with the research. It may happen. I also did this thing while I was in the beginning stage. I did think manually, and later on, from my classmate, I realized that, oh, this is the simple command. I don't need to spend so much time on this manual process. Okay, so now come to the detection part. If you have this doubt, means with certainty we never know, is there any autocorrelation problem? The first method is graphical method. If it's a time series, now I'm going to take a time series. I told you to find the correlation in a cross-sectional data in a one single variable, unless we know the combination, that with which combination we are sure that there is a correlation, there is no other way to arrange the data. So there is no possibility to find the autocorrelation in in a cross-sectional data. But if you are working on time series data, then with the lag value or with the time, you can see is there any pattern. Like yesterday, we are taking this example. Let's suppose I want to see the relation of regression of household saving with the GDP at market price. So first, I need U hat, that's the residual term, so that's come after the regression. So let first I run the regression of household saving on GDP at market price. I'm taking example of time series. For simplicity, I'm taking one single independent variable. Now, first I need residual term. Predict U hat residual. Now, those of you are from Jamia Millia Islamia, okay, I already have U hat, so it won't create U hat for new model. So let me change the name. In Jamia Millia Islamia, I think you already have good experience in STATA software. Because one of my classmates who was from Jamia Millia Islamia in MPhil in JNU, he did masters from Jamia Millia Islamia, and I had this experience that maximum commands at that time. So we took all of us will took help from him. And you told that in John Melia, you have this in coursework, right? I think in masters as well. Means you have some assignments and this data they teach you. So you have better command over this data software. So this is my experience from my friends from German Media Islamia. Okay, now I have a U hat. Now I want to see its relation with the time or with its lagged value. So first, let's see its relation with the time. The time variable we have here. Simply it's a graph. Not in PhD. Maybe in masters in Jamia there is a course because he did masters and told that teachers are teaching it in masters. I don't know about the PhD coursework, but he views as pieces in R. Okay. Okay. R. Okay. Yeah. Although yes, I also received this from many inputs that why not R? Why STATA? Then I replied that is it SPSS data or R? They are not going to change the results, right? The thing is, we need to know the process that what we are doing and why we are doing. It won't make any change whether it's e-views or STATA SPSS. So this choice is with the scholars. They can go by any software, whichever is more suitable for them. The only thing is need some consistency so that you can apply all the methods. Like let's suppose I apply 4 or 5 techniques in e-views, then 4 or 5 in SPSS and 4 or 5 in STATA. That might be then I have to know about all the 3 softwares. So besides that, if you know all the uh, one basic software and you know the maximum, how to do the maximum things in that, I think that's more appropriate. So for me, it's not think that R is better or STATA is better. Although what I found is that in R, we have to download packages for maximum commands. Means whenever you have to apply a new command. But that's the like one-time exercise. Means next time you already have installed, but for everything you have to apply the packages. That thing is not in this data. Yeah, for few things also here also we have to apply this download the packages, but not always the case. But I suggest you the source for which maximum you find in internet. Let's suppose you are doing some new thing and you don't know how to do it. If internet is helping you, that's better. And in that case, what I found is that there are so many helping hands in STATA and SPSS. Although the thing is, for tabulation, I suggest you go by SPSS because they have a this nested, I think 3 or 4 variables that can cover, but not the STATA software. I did the exercise in my MPhil. I made the table in SPSS and did all the econometric exercise in the STATA. But that don't I suggest you. For me, it's more easier than other software. That's the only reason. Uh, Although I won't make any comment on the which one is better. Whatever is more suitable for you, I think it's better because results are not going to change. Even if I'll do the same exercise in the R software, results are same, interpretation is going to be same, and model softwares are not going to tell you the models that you have to pick. So the thing is, only it's the thing that which platform you are taking. Means you are going to buy a bus, no, which bus? That's the only thing. Okay, so here we have to see the U hat residual relation with the time. So we have the U hat. I given a name U hat 1. Now I want to see its relation with the time. Is there any particular pattern? If there is any pattern, it means there is autocorrelation. Okay, so these are the results. So it might be that there is a pattern. If I can see it from, it might be that it is increasing, then it's decreasing, and then again it's increasing. So it might be that there is some pattern in the residuals. So if there are patterns in the residual with the time or its lagged value, then there is a chances of autocorrelation. Yeah, Ikra. In R, you also do this with this command window where you run this. First, you run the package with this library command, right, and then you write all the commands and that give the results. The thing is more or less it's the same. Yeah. T stat value. Oh, interpretation. Neha is asking interpretation. Neha, for interpretation, in the third part, I already interpret all the results. So go by those lectures. In the third part, we did this in detail. This table, I think we were talking about, right? We spent 10, I think 6 or 7 lectures only on the interpretation part. Means in the third part, what we actually started, we started with this coefficient, derivation of this coefficient, then derivation of variance, then derivation of all these test statistics, then R square, adjusted R square, then F, and all these values which are required for the F, and then interpretation. So we spent 7 or 8 lectures only on this part because this interpretation is very crucial. So we did this, not only this derivation of all these parts, but also the interpretation part. So you have to go with those lectures. You will find all the interpretation of all these values, what these values are, what these degrees of freedoms are, what these t statistics are, how we interpret these results, how we calculate these. So we did this interpretation, calculation, derivation, everything in that part. So just go by those videos, you will find all these interpretations. Okay, so in this case, we have some pattern of you had with the time. So it means there are a relation with the time. So it means there is a pattern in the residue. It's not random. The simple thing, it's not random. There are patterns that indicate there is a autocorrelation. So that's what we see in a graphical method. With the time, there are patterns that might indicate there is a autocorrelation. Then another thing you can see is relation with the lagged value, whether it's a positive correlation or it might be a negative correlation. So for that, we need a lagged value. So let's first generate a lagged value. Yeah, those of you also doing it first time. For the maximum, this source for this data commands and all means although it's, I think now 90% is already available in internet. Like this one is the YouTube for basic commands. Then IDRE site, which now providing you commands for STATA, SPSS, R, and I think Python as well. I'm not sure about the Python, but for STATA, SPSS, and R. And besides that, there are so many PPTs you will find in internet for different this econometric commands on internet. This LSC modules now I think available in internet free of cost. So they have all these econometric course command part, the practical part, the tutorial part. I think now they are sharing. So that's also one of the source for this STATA. Then there is a help command here which provide you all this PDF documentations. Similarly, in the internet you have all the detailed PDF documentations of STATA. So that might help you in the command process if anytime you need some command. That's and the major sources, STATA website itself. There you find maximum commands. I think I already shared it. It's now software is not more a limitation to learn. By the time I think it's already so many videos and content in the internet. Only the thing that is not in the internet is the process. That why that particular thing and how you interpret those things. That's only you have, and for that you have to read and understand. There is no shortcut for that. Yeah, in this data, if you go by this data website, That's also a source, means if anytime you are missing something. I think Rima, you got software. If not, then try here. It's the trial version. I think they provide trial version for 30 days. I'm not sure, but here you can just try it. There is, I think, trial version for 30 days that STATA always provide. It might be 14 or 15 version. I'm not sure, Rima, but because you are saying that you have this problem with the iPad, right? So then you can try with this trial version. So here in the support process, you have this video tutorial, free webinars, and so many other documentations. That's the source for this STATA. Okay, so we have this pattern. Then again, you can look this pattern with the lagged value. For lagged, the command is like I need a lag of this u hat 1, just u hat 1. It's under within a bracket underscore n minus 1. If it's n minus 2, that will give you 2 t minus 2, t minus 3. So this n minus, if you change, that will give you the lag values. So now I'm changing the name because we already have this lagged value here. I want to see its graph of residual with its lagged value. Is there some pattern? No, because this is a small data set, a few number of observations. So it's not clear that whether it's some positive or negative. But now that's the thing with this subjective methods, right? We are not certain whether is it or not. So that's why we have to check. If it's let's suppose you have a 30-40 years data and to find some direction like this in this example, these like you have this particular direction, it might be positive or negative, but that might give you a hint that our residues are related or not. This is the graphical method. Then there is a one non-parametric method. Now first just understand the idea behind this method, that how they applied this method. Today I only take this method and one more method, doesn't works in. Others I take because I think it's already 4:30. Okay, so the idea in this method is whether residuals have random values or is there some pattern. For example, generally we have this regression line and all these values, this deviation of the actual values from the regression line, that will give us the residual, right? These are our u hat values. Now if it's random, so it might be that you had, like in this case, okay, let's take these cases 1 2 3 4 5 5 6 7 8. I'm just taking hypothetical. Okay. So initially it's negative, then it's positive, again it's negative, then positive, negative, positive. So that's the means hypothetical case that this residual is random. So there is no correlation, no pattern in that, right? But if there is some pattern, like initially it's negative, 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 but that means is that initially all the residual values are negative, then it's positive, then again it's negative, like some pattern, then positive, 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 then again negative, negative, negative. So this is the picture where this is random, right? Randomness, so there is no autocorrelation. But if there is some pattern, that may indicate there is some chances of autocorrelation. Now this thing you can, okay, yeah, this is the only test. Now, although it's not designed for cross-sectional data, but this is the only test you can try on cross-sectional data, because here correlation is not required based upon two different data sets. So in for correlation, if you ask me an answer, this is the only method, and this is a non-parametric method. Although it's not a correlation technique, but this is the only method that you can apply on cross-sectional data. that you can do. Okay, so the idea is, if is there some pattern, there is a correlation. Sorry, yeah, there is a correlation of ut with ut hat, sorry, ut minus 1. Okay, means if there is some pattern, like here negative, positive, any pattern, then there are chances of autocorrelation. So how we can measure it? We have to divide it in two parts. First, total number of observations, then number of positive symbols, then negative symbols, n1, n2, and r is the number of runs. Like, let's suppose this is the data set, actual data set, and this is the pattern of data. Initially the residual is negative, then positive. Means what positive means is that above regression line, then negative below regression line, because y minus y hat, if y hat is greater than the y, that's when we get negative values. So runs here are patterns. First, 1, 2, and 3. There are 3 runs here, and n1, n2 is positive and negative. So in this case, positive runs are sorry, negative 19 and positive 21. Is it the case or opposite? N1 is the positive symbol, N12 is the negative symbol. So N1 positive is N1, the number of minus is 19, and the N2 number of plus is 21, and run is 3. Now how we decide whether autocorrelation there or not? So for that the rule is, first we have to calculate this expected value of run, that is average of this run, and then variance of this run by these two methods. And then if this number of runs, like in this case there are 3 patterns, negative, positive, negative, if that this run will lie in this confidence interval, that means there is randomness, and that's the null hypothesis, so there is no autocorrelation. Do not reject the null hypothesis of randomness. Randomness means there is no autocorrelation with 95% confidence if R, the number of runs, lies in the preceding confidence interval. If you lie outside this interval, that means there is autocorrelation. Like in this example, the average is 10.97, variance is 9.69, and if we apply this confidence interval method, the range is 4.8 to 17.7, and 3 won't lie in this particular range, so that means there is autocorrelation, because then we have to reject the null hypothesis. Null is there is randomness, means there is no autocorrelation, and alternate is there is autocorrelation, if there is no randomness. So in this case, 3 is not lying in this particular range, so we have to go with the alternate hypothesis, that is there is autocorrelation, and that's visible here. Like the pattern is like this particular pattern, negative and then all positive, like this pattern, that indicate autocorrelation, right? It means there is a relation of one residual with the another residual. This is the run test, and this is the only method you can apply on cross-sectional data. In STATA, how can you apply this method? You have to just run this command, run test, and your lagged variable. We have a, in my case, my lag values you had one, whatever name you have given, run test. So it will give you n1 and 2 number of runs and final result here. But this particular result is not this confidence interval approach. Here they apply a z test t-test approach means the different. There are three methods like we did: test of hypothesis, confidence interval, and p-value approach. So they give you results and a p-value. Concept of run, again, just the concept. Concept is that Ikra, if residual has some pattern, means that first it's below regression line, means some pattern is there, then continuously it's below regression line, then our residual, all the values are above regression line, and again then our residual, actually this gap is actually a residual, right? This is the, this gap we say u hat, right? Like it's one, then it's second u hat, then third u hat. So if it's continuous first, fourth, continuously negative, it means there are some pattern in the residue, and then it's positive, again negative. If it's random, like this situation, means it might be that initial two values are negative, then positive, then again negative, then positive, then negative. Means if there is so much randomness, more the runs, means this is first run, second run, third run, fourth run, fifth run, more runs indicate that there is a randomness and there is no pattern. So there is no correlation of one residue with the another. Like here, there are 9 runs. Let's suppose if there are 9 data sets, 9 years data, and there are different negative, positive, negative, positive. So there is a randomness. But if let's suppose we have a 30 years data and we only have a 3 runs, 1, 2, and 3. That indicate there are patterns in the residual, and that pattern may be because of relation of one residual with the another. So that's the case of autocorrelation. Ikra, is it clear? The concept of run? Okay. Okay, yeah, I was talking about that STATA will provide you answer in a run test in a p-value form, a p approach. The p-value approach is generally that if p-value is greater than the level of significance, we reject the null hypothesis. That's the p-value approach, right? So here the p-value is 0.43, and let's suppose our confidence, sorry, this level of significance is 0.05. So here p-value is greater than the level of significance. So we have to reject the null hypothesis, and null hypothesis here is there is randomness. So there is autocorrelation. Like we have seen in this graph, there is autocorrelation, right? So in this case, with the run test, it's indicating that there is a although here there are 7 runs, 7 times this data is changed. If you can look this u hat, u hat 1. Yeah, first is negative, then positive, then negative, then positive, then negative, then positive, negative. Although 7 times this in this 15 years data, 7 times this thing is changed, but still there is a chance of autocorrelation because of a p-value is greater than the level of significance. Oh, sorry, I interpreted it incorrectly. If p-value is greater than the level of significance, we have to accept the null hypothesis. So in this case, there is no autocorrelation. Like this, it was not clear in this graph whether there is a positive correlation or not. So, but by this particular run test, the in 15 observations, if there are 7 runs, means positive, negative, 7 times position is changing, that's indicating some randomness. So if p-value is greater than the level of significance, we have to accept the null hypothesis. And opposite, if p-value is less than the level of significance, then we have to reject the null hypothesis. So in this case, there is a autocorrelation. So this method is you can apply on cross-sectional data. There is no other method that you can apply on cross-sectional data because we don't have two different series, and this is the only non-parametric method which work with one single series, that's u hat. This is the only source for cross-sectional data for detection. Okay, so this is the non-parametric method. Then there is a parametric methods like this Derwin-Watson test. Now these tests I think mentioned in basic statistics books also. They describe this particular method. Now all these tests, run test onward, all the tests are at least need two different series to test the relation. Like here, this particular test is designed with ut minus 1 with the lagged relation. If there is a relation, then there are chances of autocorrelation. So first, you have to understand this method. This formula is just, if you can see in simple form, this is just in form of some correlation method. Now this is the D value that will tell us whether there is a uh, association of two residual terms or not. So first we have to run the regression, but there are conditions here. Like in the run test, yes, there is one condition that at least for n needs to be greater than 10 for both the two, positive sign and negative. But it means that, let's suppose you have a 15-year data, like in this example that we applied. In both the cases, n is less than 10, so it's not appropriate here that we can apply the run test. That's the limitation also, that at least we need n greater than 10. So in this case, we applied this run test, but it's not applicable because it needs some large data sets. Like at least you need 25-30 years of time series data. And then if you have this condition that in both the cases you have n greater than 10, then only you can apply the run test. Similarly, in the Derwin test, there are few limitations or assumptions that you have to first fulfill. Okay, before that, this method, this D value we have to find, and based upon this D value, there are rules of autocorrelation like this. This D value we have to calculate. I'll come it later on, but this lower limit of T, upper limit of T, but this D, Derwin-Watson statistics, that we have to calculate, then we can generalize whether there is autocorrelation or not. This is the method. So for that, what we need is first, we need U hat. If we do manually, we need U hat that we will get after running the regression. Then lagged value of U hat. And with that, we can calculate the D statistics. In STATA, you are not required to calculate this because there is a direct command to this method, that is dw stat. Yeah, dw stat. So it directly give you this d stat value, means this particular value, and based upon that we have to generalize this whether autocorrelation or not. First, understand these limitations or assumptions. You can only apply Derwin-Watson's test when you have intercept in the model. Second, X are non-stochastic, like generally we have in the OLS models. Third, only first order autoregressive scheme, like in Derwin-Watson test, it can only see the relation of UT with UT minus 1, not with the UT with UT minus 1, UT with the UT minus C. That's not possible. That's the limitation of this method. And fourth, residual term needs to be normally distributed. If these conditions will fulfill, then you can apply. Yeah, one more thing. We can't put lagged value of dependent variable in the model. So if by chance, like in the consumption, we have consumption depends upon consumption of last year. So in that case, we can't apply this because that's the case of autoregressive models that we will do in detail. In that cases, we can't apply this Derwin-Watson test. and there are no missing observations in the data. So many times we have this missing observations for yearly data or quarterly, but that then you can't apply this particular DW stat. So these things we have to keep in mind before applying this double Watson test. So once we apply this test, like in our case, this D value is 0.912093. We have a 2 explanatory variables and 15 observations. Now the thing is it indicating autocorrelation or not? How you can get that thing? For that thing, you have to understand this process. Just open the bracket, ut square plus ut minus 1 square minus 2ab in this numerator term. Just open this bracket and you will get this thing. Now, how you will get this thing? Actually, from the data, if you can see, this ut and its lagged value is nothing. They are same values, right? These values are the lagged values, right? Only the difference is of the one observation that is missing in the lagged value. So besides that, all the observations are same in the u hat its lagged value. So we can take as approximately same, right? Ut minus 1 square is equal to ut hat square. Approximately they are same. Why? Because except for the one observation, all the other observations are same in both the cases, because this variable is only a lagged variable of this same variable. So all the values are same, so their squared values are also same. So they are approximately same thing. So if we can write this as a 2 summation ut hat square, so and that divided by summation ut hat square, so that's 1, and minus this term summation ut minus and ut minus 1 upon summation u hat square. Is it clear? This part, anyone in doubt in this equation? This is because this both the values are approximately same, except for the one observer. And if it's, let's suppose you have a data for 100 years or 50 years, and except for one value, all the values are same in both the variables. So there is no change. So based upon this, and if we write it as a row, so the rule is now this row is a correlation of this ut with the ut minus 1, right? So the maximum case is that there is a perfect correlation, that lagged value perfectly define ut hat. So in that case, if it's a 1, if you can put here it's a 1, then d value is 0. That's the case of this autocorrelation, right? So if we are nearby 0 here, it means there is a positive autocorrelation because rho is positive, right? If you can put this negative rho, means if there is a negative correlation between these things and it's perfect correlation, if you put minus 1 here, then it's 2 into 2, 4. So that's the case of another extreme value that will indicate negative autocorrelation. Because 1 is indicating perfect correlation, right? So if there is a correlation, there is a autoregression. So the thing is, if it's nearby 0 and 4, there is autocorrelation. And if it's in between, like if this row is 0, there is no correlation between u hat and ut with ut minus 1, then this is the d value is 2. That means there is no autocorrelation. Is it clear? This thing I'll take tomorrow. Lower limit and upper limit. There is some indices zone here, and that I'll take tomorrow. But is it clear that if it's nearby 0, there is positive autocorrelation? If it's nearby 4, there is negative autocorrelation. Just go by this textbook. Try to understand this thing. It's based upon, simple thing is this correlation. If this correlation is perfect, there is autocorrelation. If this correlation is like 0, there is no autocorrelation. Nearby 0, this correlation nearby 0, there is no autocorrelation. In our case, the value is 0.91. The statistics value is 0.91. So that means that value is between 2 and 0. So it may be here somewhere 0.91. So is it a positive correlation, autocorrelation or not? Means is that value coming in decisive zone or not? That I'll take tomorrow. But there is an indication of autocorrelation. Is it clear? Anyone any doubts so far? This T stat. Run test, graphical method, and Durbin Watson test. This indecisive zone tomorrow I'll take it, and modified version of D statistics. That's get rid of this indecisive zone. That I'll take in the next class. Sorry, not tomorrow, but now next we have on Wednesday, because Tuesday I have one presentation in university regarding my research questions and all. So I might be occupied, but that I'll compensate on next Saturday. Again, I'll take some class. So I hope you're getting these things in detail, and that might help you in your researching. So by Wednesday, please prepare your variables list and try to work these methods in your dataset. Okay, so thank you so much. So now we will meet on Wednesday at 3 p.m. and try to do this exercise with the class on your datasets so that you will write your thesis and your data analysis in a better way. Okay, anyone any doubt or anything you want to discuss? Okay, yeah, Neha was asking this question. Uh, Neha, the limitation is like, now for that you have to understand the T test and F test. In the run test, it's not possible because why? T statistic, if we go with the T distributions, that's F distribution is for the squared variables. When you have a numerator and denominator, like compare of variances or compare of residual sum of squares of two different regressions, that we do in different type of F distribution, F tests, like compare of two unrestricted, restricted models. Means in simple terms, when you have a variables in a squared format in numerator and denominator, then you have to apply the F ratio. That's not a most probably a situation in these all the autocorrelation tests. These statistics you only apply when you have first this thing, that generally why we apply T statistics in regression models, because we don't know the population standard deviation, and if by chance our sample size is small, then we always have this solution of T statistics. But in these tests, like in this Durbin test, these tests have their own, like this Durbin Watson. It has a different distribution, and for D, in the these econometric textbooks, you will find in the end there is a D distribution table, right? It means that I want to take in the next class also. I think my screen might not be visible. Yeah, in these statistics values, like these, with whom you will compare these calculated D values. For that, we need this range, right? Lower upper limit. So for that, we have a separate D distribution, because T distribution is generally what Z distribution is for the standardized normal distribution, right? And I discussed in the first part, I think, in the hypothesis, that how we reach to this Z distribution out of n number of combinations of normal distributions. We find this shortcut and one unique answer, that one distribution that is standardized. That was the trick, or that was the solution also for the earlier problems that we are facing in a hypothesis testing. And based upon that, this students, this t-test, It's also based upon the normal distribution, but the thing is, what the change is that the interval is wider, because in small sample size, maybe that because of the biasness, the chances are that we find these results more variation. So we use the t statistics, and generally because we don't know the population standard deviation. But here in autocorrelation, there is no such method that where these criteria are fulfilling, like in these statistics. It's not a statistic like the mean test. When you apply t-tests, generally when you have a single parameter like these estimates, beta estimates, or you compare the mean in proportions, you compare generally with the z-test. But that's not the situation here, right? I mean, this is not a single mean value, right? It's something that is squared by squared and some d distribution. So it's totally different distribution. You can't apply t distribution here, nor the f, because it's not some that compare of numerator with the denominator. Then only we can apply the f test, and only if they are in the square format. So these criteria are not fulfilled. Similarly, the next methods, like I'll take that in the next class, like this Bruce-Godfrey method, where we have to see this relation of u with all the values, and there we compare this r square. Now this single squared distribution is chi-square distribution. So we can't apply the chi-square distribution on a t-stat and with the f-test. So for that, Neha, you have to go with these distributions, that when we have to apply t, when we have to apply f, when we have to apply chi-square, that will answer this thing. Means uh, go this first part videos, hypothesis testing. I discussed these in details, that when you have to apply t, when you have to apply f, when you have to apply z, when you have to apply chi-square, and when you have to apply non-parametric methods. This t distribution is totally distribution. These are actually distributions, and they're designed based upon the nature of these results. And it's not that we can apply one method on the another. No, it depends upon the distributions. Neha, then go to those lectures, because we discussed it in detail one by one, that one t-test, and we took different comparisons, one mean with another, more than two means comparison, variance comparisons, proportion comparisons, squared comparisons. Then only you can, and these distributions. I think I took 3 or 4 classes only on the history of this Z and T distribution to understand why we applied. And this is the 50% part of the statistics, inferential statistics, because this is the only method you can test your results, whether they are significant or not. So that's equally important to understand that process. So just to go by those distributions, you will get this idea. When we have to, generally these 4 distributions we apply, T, Z, F, and chi-square. But in this Durbin-Watson, I'll come tomorrow on this thing, lower limit and upper limit, because for this we have in econometrics, we have a separate table, D distribution table, that's only designed for this Durbin-Watson test. And from there we have to compare these results, whether there is autocorrelation or not autocorrelation. It all depends upon the nature of data. Mean is the single values like 5, 10, 15, 25, 1000, 1 lakh. So for that, distribution is different. Square is something different. All the values are positive, right? So chi-square is totally different. F is comparison of two squared values, like two chi-square values. That distribution is totally different, because their probability, expected values, everything is different. That's why we have a different distributions based upon the nature of data, and we apply them indirectly in econometrics based upon the situation. Okay, yeah, this question actually it's important. So thank you so much for asking this question. Anyone, anything else? Okay, so thank you so much. It's already, I think, 5. So now we will meet on Wednesday 3 p.m. Thank you so much.